It's pretty common when working with real-world data to get results in the form of a time series. For example, this input uses the country data function to get the population of Portugal between 1950 and 1970. The result is a time series expression, which is a special data structure that is used in the Wolfram language for representing time series. The actual time series data, though, is simply a set of values indexed by time, and that time series data structure is just a convenient way to represent the data. The same data could also be represented as a list of pairs giving the time and the value for each point in the series. For example, this input generates that same time series one point at a time. The result is a list of pairs giving the time in years and the population at each time. This shows the datelist plot function giving a plot of that data. The same plot can be generated from the time series expression since it is, after all, the same data, just in a different form. The list of pairs, that is, the value of the variable population list, can be converted to a time series expression by applying the time series function, which returns the same time series data structure as in the opening example. The display of that expression shows the date range of the series and the number of data points. In this time series, the time ranges from January 1950 to January 1970, and there are 21 data points, 1 point for each year from 1950 to 1970. Clicking the plus button shows some additional properties of the time series. The additional display shows that this time series has one output dimension, since there is one population value for each date, and the increment between dates is 1 year. Although the time series given as a list of pairs and the time series given in the time series data structure nominally contain the same data, there are some important differences. One of those differences is in how time is represented. Here again is the list of pairs. Time in this list is specified simply as the year corresponding to each population value. The list of times can be obtained by picking out the first element from each pair in that list. In the time series expression, the list of times is instead represented as a property of that expression. This gives the list of all of the properties for this time series expression. The property of interest here is the dates property. Properties are requested by giving the time series expression followed by the name of the property in square brackets. Instead of just giving the year, this is a list of date object expressions. This shows the first of those expressions in input form. Instead of giving just the year, each date object expression specifies the instant of time at the start of the first day of each year. A related property is the times property, which shows those same dates not in the familiar date format, but as integers giving the number of seconds since January 1, 1900. This, in fact, is how the dates are actually stored in the time series expression. You can use the from absolute time function to convert those integers to ordinary date format, and you can use the absolute time function to convert the other direction from ordinary dates into the number of seconds since January 1, 1900. Interpolation between times in the time series can also be done. This shows the interpolation function used to do linear interpolation for the time series represented as a list. A similar interpolation can be done for the time series expression by giving the time series expression followed by the date in square brackets. In that input, it is necessary to give the date as a date object expression, since the number 1960 would be interpreted as that number of seconds since January 1, 1900, rather than as a year, which is not what is wanted here. Another property of the time series expression is values, which gives the population value for each date. The list of population values is given as a quantity array expression. You can use normal to see the list of populations. Quantity array expressions provide a way of representing an array of quantities when every quantity in the array has the same units. The same list of quantities and units could be given as a list of separate quantity expressions, but quantity array provides a way to do that without specifying the units separately for each element. The quantity array expression can be used just like any other array. For example, this gives the mean of the elements in the array. That same result can be obtained by applying mean directly to the time series expression or to the population values taken from the list of pairs. Time series come up for lots of other real-world data. For example, this input uses the financial data function to load stock trading information. The string OHLCV in that input stands for opening, high, low, and closing prices and volume. The result is again a time series expression. The display shows an output dimension of 5, since for this series there are 5 values, the open, high, low, close, and volume numbers, for each date. The series can be plotted as before using datelist plot. For example, this shows datelist plot and time series map used to pick out and plot the volume data. The time series map function works like the map function, but for time series. It preserves the dates and maps a function onto the values. In that input, time series map maps the last function over the list of values in the time series expression, which picks out the last of the 5 values, which in this example is the volume data, and returns a new time series. The effect is equivalent to using normal to convert the time series data structure into a list of pairs, and then using the ordinary map function on that list of pairs to get the time and volume values as a list of pairs rather than as a time series expression. That list of pairs can be used in datelist plot to get the same plot as before. There are many other ways to plot this data. This shows a plot called a trading chart, which is a common way of displaying the opening, high, low, and closing prices and the trading volume on one plot. That plot is specific to this type of data, but similar things can be done for other time series. To illustrate some other time series operations, this input returns a time series for air temperature measurements. And here is a plot of that data. One common operation with time series is smoothing. There are several ways to do that. This shows that time series after smoothing using a simple moving average filter, which makes it easier to see long-term trends in the data. For some operations, it's useful to have the time series sampled at uniformly spaced times. This uses the time series resample function to resample this series at times spaced 1 week apart. And here is a plot of the resampled series. This uses the time series model fit function to fit a mathematical model to this time series. The result is a time series model expression that contains parameters of the model. That model can then be used for forecasting or for other analysis. The type of model can be specified in the input to the time series model fit function, or in this input the function was left to choose a model automatically. The display shows that the function chose a model called an ARIMA model, which stands for an autoregressive integrated moving average model. This shows some basic statistics about the parameter estimates in the model, and this shows the time series forecast function used with that model to compute a forecast for the next 8 time periods, which here is the next 8 weeks. The result displays with a head of temporal data, but it's actually the same time series data structure as in earlier examples, and in fact the time series expressions in those examples also have a head of temporal data. This shows a plot of the original data and the forecast on the same plot. You can find more information about working with time series in the Wolfram language by following links from this guide page on time series processing.